This is a brief overview of our paper, Train Attention Augmented Language Model, to be presented at NeurIPS 2024. This paper is written by Yeongbin Seo and the corresponding authors Dongha and Jinyoung at Yonsei University, South Korea. We propose a method to enhance the capacity of LLM for continual knowledge learning, i.e. CKL. In real-world scenarios, the word knowledge stored in the LMs can quickly become outdated as the world changes. Continual knowledge learning allows LMs to constantly obtain new and updated knowledge while mitigating forgetting of previously learned time-invariant knowledge. Our method, Train Attention, i.e. TA, is a module designed to detect important information in the document and give attention to them while learning the document. Like in this figure, the ordinary LM learns from documents with uniform weights, while the TA LM, a TA augmented LM, learns from documents with weights adjusted according to importance. By selectively learning only important information in the data and ignore unimportant part, the model can avoid unnecessary parameter update, thus reducing the unnecessary forgetting. So what is the definition of important tokens and how do we formalize it? We suggest defining token importance as usefulness, which is the novelty of our work. Usefulness indicates how much the contained information is useful for serving related tasks in the future. In other words, given a text data D composed of token X, if learning a specific token Xi can enhance performance on future tasks TD more than learning other tokens, then the token Xi can be considered more useful. Defining the importance as usefulness enables employing a meta-learning algorithm to teach TA to predict useful tokens. Let theta represent the LLM and phi represent the TA. As shown in the illustration on the right, the TA determines which tokens to focus on within the data, generating weight map accordingly. And the next step, the LM then selectively learns the document based on these weights. The learned theta solves the task TD, and the parameters of the phi are updated to maximize the task performance of theta. The TA utilizes a transformer architecture that shares the same tokenizer with theta. We test a 1 billion tiny llama or a smaller 100 million parameter BERT model. This is a weight map generated by the trained TA. An orange light highlights key information such as the subject's name, occupation, or date of birth. We mainly test on a dataset we proposed called Llama CKL, and I will introduce it briefly. This dataset contains instances that consist of a document, a question, and a label. The document is extracted from Wikipedia, and the question is a query that can be answered with short entity name using the information in the paired document. The instances are split into training data and test data. We first train the train attention phi with the train data. Then, we first test the LM, theta, with test data, and the data with correct response are categorized into the not to forget set, while the data with incorrect responses are categorized into to learn set. In the testing phase, we train theta on the documents in the to-learn set while measuring accuracy on the questions from both the to-learn and not-to-forget sets at each epoch. To-learn accuracy increased from 0 to 1, while not-to-forget accuracy decreased from 1 to 0. Each result now represents plasticity and stability respectively. Now, I will introduce the experimental result briefly. In experiments, TAALM demonstrated 4 times the plasticity compared to baselines. In other words, it learned more and much faster. Additionally, it tended to forget less, according to the right figure, which indicates the not-to-forget accuracy. And consistent trends were observed in the previous benchmark, temporal wiki, proving robustness of our method. This is the end of our presentation. Thank you.